Hi, in this video, I will be showing you problem number 40 of chapter 14, section 8. Use Lagrange multipliers to find the dimensions of the rectangular box with largest volume if the total surface area is given as 64 centimeters square. This is the same problem in the previous section 14.7, exercise 50. So first let's see what Lagrange multipliers tells us, the method tells us. Explain how the method of Lagrange multipliers works in finding the extreme values of f of xyz subject to the constraint g of xyz equal to k. To find the maximum and minimum values of f of xyz subject to the constraint g of xyz equal to k, assuming that these extreme values exist and gradient g is not equal to 0 on the surface g of xyz equal to k, first find all values of x, y, z and lambda such that del f xyz equal to lambda times vector del g xyz. This means the gradient vector f is parallel to gradient vector g, along with the constraint g of xyz equal to k. And next step, evaluate f at all points xyz from step A. The largest of these values is the maximum value of f, and the smallest is the minimum value of f. The number lambda is called the Lagrange multiplier. In other words, the maximum or minimum occurs when the gradient vector f and gradient vector g are parallel from step A. So let's start with the rectangular box with the dimensions x, y, z. And the volume of the box be f of xyz, that is our objective function, which is xyz, x times y times z, which is length times width times the height, where xyz are the dimensions of the box. And we are given the surface area, that is kind of a constraint in this problem. And the constraint is the surface area, which is g of xyz. Surface area involves the same area at the bottom and the top. Two faces are of same area, and then two other faces are of same area. So it will be 2 times xy plus 2 times yz plus 2 times xz. By common factoring the two out, you get 2 times xy plus yz plus zx. That is given to be 64. So if you solve for xy plus yz plus zx, which will be just 32. So this is the constraint function 2. The regular function, the objective function, where the volume is the largest, the maximum volume is f of xyz, which is equal to f of xyz equal to xyz. So we have these two. Now we have to apply the Lagrange multiplier method by setting del f equal to del g, or nebula f equal to nebula g. So Lagrange multiplier method. So set del f equal to lambda del g, which is component form f sub x, f sub y, f sub z equal to lambda times g sub x, g sub y, g sub z. They are all partial derivatives with respect to x, y, z. So using our f of xyz as xyz and partially differentiating with respect to x, y and z, we get yz, xz, xy equal to lambda times. So you are going to differentiate this partially with respect to x, y and z for each component. That will give us lambda times y plus z, comma, lambda times x plus z, comma, lambda times x plus y. So we have these two vectors equal. So compare the corresponding components and equate them. Yz must be equal to lambda times y plus z. Call it step A. And then xz equal to lambda times x plus z. Call it step B. Then xy equal to lambda times x plus y. Call it step C. There are several ways of solving these three equations. Now we are going to apply a method where we are going to subtract b from a and get one relation. Same way c from b and get another relation. There are multiple ways by which you can solve these three equations. These three equations a, b and c. I'm going to consider a minus b. This gives yz minus xz from the left hand side equal to lambda times y plus z minus x plus z in parentheses. So z times y minus x equal to lambda times y minus x. So common factoring the y minus x, you get either x equal to y or z equal to lambda. Now if lambda equal to z, there are two possibilities. We saw two possibilities. If we pick lambda equal to z, if you substitute that into the relation lambda times y plus z equal to yz, and we substitute lambda equal to z here, you get z times y plus z equal to yz. This would mean z square equal to 0. Yz will cancel out. So z square equal to 0 or z equal to 0, which is false because z is one of the dimensions of the box. So dimension cannot be 0. So we have to disregard this possibility. So x equal to y is the only option here. So we got this x equal to y by considering step A and step B and subtracting them. Same way we can subtract step C from step B. By similar reasoning, we can do B minus C, and this would give x times z minus y equal to lambda times x plus z minus of x plus y. This would imply x times z minus y equal to lambda times z minus y. This would give us two possibilities. Either lambda equal to x or y equal to z. Either y equal to z or lambda equal to x. Similar to the way we disregarded lambda equal to z, we can disregard x equal to lambda as well. So if we choose lambda equal to x, substituting this lambda equal to x into the relation lambda times x plus z equal to xz, we get x times x plus z equal to xz. This would mean x square equal to 0, which would mean x equal to 0, which is false. So the only possibility is that y equal to z. So we already proved x equal to y. Now we are proving y equal to z. Using x equal to y and y equal to z, we can say x equal to y equal to z. all the three sides of the box, all the three dimensions of the box, namely length, width and height, are the same. Substituting x equal to y equal to z into the volume relation, into the surface area relation, xy plus yz plus zx equal to 32, we get 3x square equal to 32, or x square equal to 32 over 3, or x equal to square root of 32 over 3, which is 4 times square root of 2 over square root of 3, multiplying by square root of 2, both numerator and the denominator, we get 8 over square root of 6, or x equal to y equal to z equal to 8 over square root of 6 centimeter. They are the dimensions. So the dimensions of the box are, all the dimensions are the same, which are equal to 8 over square root of 6 centimeter each. Hope this video helps.